This is homework 3, part A. In this video, I will explain how to find the null matrix required for Buckingham pi method to find our dimensionless values. Now, in our case here, we'll be looking at a fluid flowing through a pipe. So, to describe the flow of our fluid, we can use 6 different physical processes. So, our first and most straightforward will just be the length of our pipe here. We'll also use the diameter of our pipe, as well as our change in pressure, the fluid's viscosity, how fast it's moving through the pipe, so our velocity, and the density of our fluid. Now, in order to perform our Buckingham pi method, we'll look at our matrix. So our matrix will use 3 SI units to describe all 6 of these physical processes. Now these can be broken down into our length, time, and mass, which we'll just use as, for our mass, we'll say kilograms. For our distance or length, we'll say meters. And for time, we'll say seconds. So, we'll put our physical processes up at the top here. Oops. Okay. So, each of these processes will describe what units they'll be in. For our 3 SI units. And I'll assign them colors. Okay, so our length and a diameter are the 2 most straightforward. They will just measure our length and our diameter, which will only be in units of meters. There's not much else to them. For our pressure, change in pressure, or a pressure drop, pressure is in units of pascals. And we know that pascals or force, pascals or pressure, describes force per area. So say F over A. And according to Newton's second law, we know force is equal to the mass of an object times its acceleration. And its acceleration can be described as meters per second squared. So with that, we'll have our force as kilogram meters per second squared. And since this is divided by an area in our pressure drop here, our F over A will be described as kilogram meters per second squared per meter squared, as we know area will be meter squared. So canceling out our units here, we'll be left with kilograms per second squared meters. So using our SI units of kilogram meters in seconds, pressure drop can be described as, see, keep colors consistent, kilograms over seconds, it's red, second squared meters. So we know our viscosity describes pressure throughout a time. So we use that. We'll say pascals times our seconds. So using our SI units derived from our pressure drop, we could say that our viscosity is in SI units of kilograms per second meters, because we're multiplying out seconds in the numerator, so the square will cancel. Okay, our velocity is just in meters per second. And then finally, our density we know is our mass over volume, which is kilograms per meters cubed. Okay. Which kilograms per meters cubed. Now, in our matrix here, we will describe each of the power values as a number. So, for example, length. Length is in units of meters, so that can also just be rewritten as meters to the first power. So we'll give our length units in 1 meters, and then 0 kilograms in 0 seconds. Our density is the same thing. Our pressure drop is in kilograms per second squared meters. So kilograms will be 1, and then seconds will be -2, and meters will be -1. Our viscosity will be kilograms, meters -1, and seconds -1. Our velocity is meters per second, so we have no mass SI units there, so that'll be 0. Meters in the numerator, so 1, and then seconds in the denominator, -1. And lastly, our density will be kilograms in the numerator, and then meters cubed in the denominator, so -3 there. Okay, so in order to find our dimensionless values using this matrix, let me get this out of the way actually. Whoops. Put this right here. We'll need to multiply this matrix by what we call a null space. Now, multiplying this matrix by a null space will give us our SI units as zeros across the board. So we will be unitless. This will be a unitless value. So, for example, Reynolds number. So there's an infinite number of values in this matrix, which we'll just say C1 through 6. And calculating them we'll have to do in Python, because it's going to be a little tricky by hand. Okay, so to continue on further with the Buckingham Pi method, we can say that we'll have to constrain a few variables, a few of our physical processes, which we'll describe as pi for Buckingham Pi. And to get that, we'll say that that'll be equal to the number of physical processes that we have, which we'll call n, number of physical processes. From that, we'll subtract our SI units, which we'll say is M, and we'll call those SI units. So in our case, we have 6 physical processes and 3 SI units, which means that we need to constrain 3 different variables to use the Buckingham Pi method. So we'll just pick 3 different variables, which we'll say we'll use length for one of. Let me choose different color. So constrain 3 variables. So we'll say length. We'll do viscosity, and we'll do our pressure drop. Okay, so because we're considering 3 variables, we'll have 3 different Buckingham Pi equations. So we'll say pi 1, pi 2, pi 3. So our 3 constrained variables will appear each in one of the 3 equations. So writing out our first equation, we'll say length will appear to a power of 1. Since our viscosity, since length appears in the first equation, it will not appear in the second 2 equations. So we'll put it to a power of 0. So it'll be equivalent to just 1. Our viscosity and our pressure drop will also not appear in the first 2 equations because we already have one of our constrained variables. Say our viscosity does appear in the second equation, put that to a power of 1, and does not appear in our third one, but pressure drop does. Now, we'll need to multiply this equation by the remainder of our physical processes. So diameter, velocity, and density in each of the equations. So each of those, or diameter, velocity, density, each of those will be multiplied by an unknown power to us currently because we haven't solved it. So we'll say diameter A, velocity B, density C in the first one, and then D, E, F, G, H, I. So using this method, we will be able to use the Buckingham Pi method in order to find our unknown. So now we can calculate the null space of our matrix in order to solve for the pi variables. So to start, we'll need to import numpy as np and import scipy as sp. And this will just be to be able to run our calculations. Okay, so using that numpy, we can create our matrix. So we'll say our matrix A equal to np.array, and with that we can type in our matrix. So reading from left to right as our length, diameter, change in pressure, viscosity, velocity, and density. Starting with our kilograms, we have 0 for our length, 0 for diameter, 1 for our, oops. Oh yeah, okay. So 0 for our length, 0 for diameter, 1 for pressure, 1 for our viscosity. We'll say 0 for pressure for velocity, and then 1 for our density. And then we can say for our meters or length, so length is 1, diameter is 1, or diameter has 1. Our change of pressure is -1, since it's in the denominator. -1 for viscosity, 1 for velocity, and -3 for our density. And then we'll say for our time or seconds, 0 for length, 0 for diameter, -2 for change in pressure, -1 for viscosity, -1 for velocity, and 0 for density. Okay. So, maybe. Okay, so then with that, we have our array A, which is all right here. Okay, so to conduct our null space, we'll say variable ns is equal to SB, our math program, linear algebra, and then null space of matrix A. And we can look at what that looks like. Okay, so this is just a set of vectors that we can use the dot product to find our values of 0 of our matrix. So we'll use this to solve for our dimensionless numbers. Okay, so to solve for our C1, we'll say C1 is equal to null space, numpy, linear algebra, ns for our null space, and solve ns for null space, and we'll say for our three physical properties that we're looking at, so length, change in pressure, and viscosity. And here we would input the position where they're in our matrix. So for length, that would be 0, 2 for change in pressure, and 3 for viscosity. And then we will create an array for that. And we'll say, starting with our, when we set each value to power of 1, so we'll start with our length. So we'll say 1 for our length, and then 0 for our viscosity and change of pressure. And see what that looks like. Taking the dot product of this matrix here with our null space NS will give us the power values for our first non-dimensional number. So for dot product, we'll say C1 dot product will be @ S. Or wait. Right. And with that, we'll say, again, this will be in our position. So this first position will be length, second diameter, third change of pressure, fourth will be our viscosity, and then this will be our velocity and our density. So this is our pi1 value, and write this in. So our length is at a +1, so that'll be in the numerator, and our diameter is at -1, so that'll be in the denominator. And then the rest of these values are so small that they're basically 0, so we just won't include them. So our first dimensionless number will be length over diameter, which, bringing it into our SI units, makes sense because that'll just be meters over meters. So to find the remaining two, we can copy this. So we'll call this one C2. And everything will be the same, except in this case, our length will be set to 0 and our change in pressure will be set to 1. So running that, we'll see what our C2 value looks like. So this is what we'll multiply. We'll take the dot product of with our null space. So we'll say NS at C2. Run that, and we'll get these values. So we can see that for our pi2, we'll have 0 for our length and 0 for our diameter. Our change of pressure is 1. So say P in the numerator. Our viscosity is also 0. Our velocity is at -2. So that'll be v squared in the denominator, and our density will be -1. So it'll be rho v squared in the denominator. And that will be our second dimensionless number. Okay, so our third one, say C3 here, and 0 for our length, 0 for our change of pressure, 1 for our viscosity. We'll run that and find our C3 value. And then take the dot product and see what we get out of this. So our third Buckingham pi number will be 0 for length, -1 for our diameter, 0 for change of pressure, 1 for numerator. 1 for viscosity, -1 for velocity, and -1 for density. So what we'll get is our viscosity, so mu in the denominator, mu in the denominator, in the numerator, and diameter times rho times velocity in our denominator. And that is how we can solve for these dimensionless numbers using the null space.